Yeah, we'll start in a few seconds. We have people from the very east of Canada and people logged in from the very west of Canada and then from the very south of the US. So it's a really nice thing to see these event bringing people together, I would say. So So John and the Meshworks team, you guys are not muted, so I'm just gonna...
No, we are live, you know.
Yeah,
so
yeah, that's good.
I'm going to mute my mic just so that there's no background noise. Okay.
Yeah, thank you. Okay, so I have the guys here. Let's kickstart this lunch and learn. So thanks a lot, folks, for coming together. I'd like to thank the Aventec team, the Wolfstar Technologies team, as well as the Detroit Engineering Product team. Thanks a lot for coming along and helping supporting this event. It's really appreciated. It's one of these series of multiple webinars that we're planning to do like by next year. So it's called Industrial Challenges. So the main subject that we're going to be tackling today is getting accurate mesh and accurate loads for the next 2 hours. First, we're going to be joined by the AP Meshworks team to showcase of the capabilities of Meshworks, and then followed by TrueLoad. I'm just gonna start with a quick presentation, and then I'll handle the ball to the John, the TrueLoad, the Meshworks team. So as we know, innovate, be competitive, and accelerate the go-to market are some of the industrial challenges that we're facing more and more today. And being able to leverage the power of the simulation tools to overcome some of these issues become rather a necessity. A lot of the time, CE engineers and analysts face usually the challenge, and they face the challenge to get like more accurate results, but also on time. Here, hence the need for a state-of-the-art tool to fulfill their tasks. Amongst most of the challenges, or many challenges that the engineering community would face, is getting more accurate mesh that will replicate accurately the engineering geometry, and as well as knowing the field loads. I would say like at a primary design stage, as well as during the product development stage, or also throughout the whole product life cycle, the analysts are faced with more challenging of getting complex geometries replicated through a mesh and then imported to the proper FEA or CFD tool. These tasks can most of the time be tedious, depends on the complexity of the geometry, and without compromising with simulation quality, these tasks become more and more challenging sometimes. From another end, I would say like from different perspective or for different industries, from aerospace to automotive industry and from oil and gas even to industrial equipment. One of the most challenging tasks for analysts is to develop specific load cases for their FEA models that matches the measure of strain values. Typically, it will take days, sometimes weeks, to develop the right load cases that matches basically one or two strain gauges in a single point at a time. So during today's Lunch and Learn, we're going to try to answer some of the challenges that faced by the engineers community, mainly how to shorten your pre-processing time, how mesh level morphing can save time and cost, how to optimize the strain gauge's position, and how to apply accurate field loads and for accurate fatigue life calculation. For that, we have a panel of experts today. So from Aventec will be myself, and then during the second segment of today's Lunch and Learn, we're going to be talking about pre and post processing across industries, a presentation of Meshworks. We have a panel of experts from Detroit Engineering Products. We have Radha Krishnan, the president of AP. We have Ray Cheney, the director of software support, and also we have John Gilmas, he's the director of business development. And then during the second segment of today's presentations, we'll be talking about do you know your loads? A presentation of True Load from Wolfstar Technologies. We'll have Tim Hunter as the president and Susie Ralston as the business development manager. I'm just gonna do like a quick presentation of Meshworks and True Load, and then I'll pass the ball to the DEP team. Just a quick word about Aventec. A lot of you guys would know us as software provider or reseller, but we are more than that. Our main objective is to identify discrete, underutilized, and inefficient processes and help companies evolve the silo culture to transition over to processes that encourage clarity, visibility, traceability, and high organizational efficiency. AP Meshworks is an integrated CAE platform for pre and post processing involving rapid concept CAE and CAD model generation, parameterization and optimization, advanced meshing, process automation, and concept modeling and morphing. As for True Load by Wolfstar Technologies, is a first-to-market solution that leverage FEA models to place strain gauges on unmodified physical parts and then back calculate load. True Load directly interfaces to FEA fatigue software such as FESafe to make FEA-based fatigue with correlated loading events a natural part of the design cycle. I would like to thank the attendees here that make it here, although the traffic, I believe, was horrible in the snow. And I would like to thank our attendees through the GoToWebinar. And I would like to thank our presenters in advance. And John and the DP team, the ground is yours now.
Okay, great. Thanks, Hisham. If you can pass the ball to me, I'll share my screen and we can get the presentation started.
Yeah. Here you go.
Okay, all right, great. Once again, thank you, Hisham, for that nice introduction. And I would like to really thank all the participants and presenters today for your time. I'll directly jump into our presentation. I hope everyone is able to see my screen. My name is Radha Krishnan from DEP. I'm responsible for all the software product development and also the engineering process development. Our goal and our vision is to accelerate and transform the product development process through continuous innovation. And anything and everything that we do at DEP is all about how to reduce your product design and developmental time, and also how to optimize your products. to meet all your design performance criteria, and at the same time, how to make it lightest weight and lowest cost possible. And we achieve all that through our innovative platform, CAE modeling platform, which is Meshworks, which is what you'll be hearing more today about. And DEP is based out of Troy, Michigan. That is where we are headquartered. We're close to about 170 employees in Michigan and in California together. And globally, we are about 500 engineers. And we are into engineering services as well as software development. But today's focus is going to be on Meshworks. I'll quickly skip this slide. This is a brief history about ourselves. Really, our global offices, whether it's North America or Europe or Asia, we support our customers every day with our blessed team of about 500 engineers across different industry verticals. So today we support customers in all the major industry portfolios, whether it's automotive, aerospace, heavy equipment, oil and gas, etc. A brief or a partial list, I should say, of all the customers that we work with on a daily basis. So all major OEMs, tier one suppliers, etc., spread across all the industry verticals is whom we support with our Meshworks platform. This is a growing list, and we are very glad to say we are celebrating our 21st year as we speak, and our solution, which is Meshworks based, has been tried, tested, and proven across major OEMs like a Toyota, Nissan, GM, or Airbus, or Boeing, etc., or BW, XT, regardless of the kind of industry that you are looking at, Exxon Mobil, and so on. Different industry verticals, the major OEMs and suppliers are our customers as we speak, who are using the Meshworks solutions on a very regular basis. Now, with that, I will right away take a deep dive into what Meshworks is all about. So Meshworks is, as Hisham put it, it is a parametric CAE modeler. From CAD data, if you build the model, it becomes parametric. It has got excellent morphing technology, which can be applied to both CAE models as well as CAD models to rapidly modify the designs. And the parametric models can then be linked to optimization schemes, whether it's a parametric abacus model or any other solver model or a CFD model like a star CCM plus model, can all be parametrized and linked with optimization tools like iSight, and you can get your optimum. You will hear more about it as we move on. And we also have our process automation environment with which you can automate a lot of your day-to-day processes. It has an excellent pre- and post-processing capability for rapid results extraction, like a stress or fatigue safety factor, etc., from the results that come out of the analysis. And of course, our ConceptWorks, which is a new addition with which you can create early stage concept models when there is zero CAD data whatsoever. Okay. So this is what Meshworks is about. Now, with that having said, how does Meshworks fit in the overall product design and development cycle? If you look at this map, the traditional place where CAE fitted in is defined by this blue curve. What you see on the x-axis is any product development going through its concept stage, detail stage, and then once the hardware becomes available, the validation and verification and subsequent maintenance and whatnot. All right. So typically CAE was largely used in the detailed engineering phase, but more and more in the last 5 years or so, CAE is being pulled way ahead during the early concept stage of the modeling itself, of the design and development itself. So this is where, if you look at Meshworks, Meshworks can help you create quick concept models, whether it's automotive, aerospace, etc. You can take existing models, CAE models, and then quickly morph them and get your new concept models very quick, or from zero CAD data with very basic design information like cross sections and trajectories, you can create a brand new CAE model with no traditional CAD becoming available. So generating quick concept models, FE models, is a major advantage of Meshworks, and then it becomes parametric inherently. So which means on the fly, you can modify the dimensions at the CAE model level itself. What you see up on the screen here, these are all animations of CAE models. And why it should be parametric? Because it allows you to subsequently run several iterations, like a design of experiments or an optimization and so on, so that you can achieve an optimized design even at a concept stage. So the ability to rapidly create your models, parameterize them, and then optimize them is nicely achieved during the concept stage. And at the same time, if you're in the detailed engineering phase, during which time design now takes the lead more than CAE, where all your traditional UG, NX, or CATIA, or SolidWorks, the design is driven more by traditional CAD. At that time, you want to convert a CAD to a finite element model in the shortest time possible. That is where Meshworks has all the advantage to do that. And the moment you create such a model in Meshworks, it being inherently parametric, it allows you to do one more round of optimization, or many more rounds of optimization. And as the product development cycle progresses into the hardware stages, naturally CAE role also starts to diminish. Now, in this whole process, Meshworks addresses adequately well with our morphing and concept modules during the early concept stage, and all our parametric CAE and topology optimization modules address your concept and detailed engineering phases very well. And our rapid meshing and model assembly modules address the entire product design cycle time extremely well. So this is how Meshworks nicely fits in your overall framework. Now, Meshworks also has some key differentiators. I already talked about the parametric modeling capability, wherein the moment you mesh it, it becomes parametric. And at the same time, it is also an integrated modeler, which means from one database, you can simultaneously generate a durability model for stress analysis with very detailed finite element meshing, the connections defined with detailed bolt modeling, etc., and contact modeling. So as we all know, for durability and stress analysis and fatigue analysis, the devil is in the detail. So Meshworks can, from one database, simultaneously generate a durability model and at the same time a vibration model, for example, which tends to be in general much more coarser, and the connection scheme could be different, and the entire modeling technique itself could be different. So you can templatize an attribute for durability, a template for noise and vibration, and from one database, you can generate multiple models. So this way, you can really reduce your model building time. There is no duplication of effort having to repeat both the kinds of modeling. All right. And when it comes to the parametric modeling, it can go down to the detail of varying a wall thickness in a complicated tetrahedral model, or in a sheet metal assembly, take at an assembly level, taking a width change or a depth change, etc. All that can be done very effectively with a parametric modeling. Meshworks is also an associative modeler. So as the design keeps changing, for example, week 1, the design doesn't have any ribs, and week 2, you have ribs. Meshworks tracks all the design changes and automatically, surgically updates your finite element model. So which means you don't spend too much time regenerating a new FE model as the design keeps evolving. All right. And our associative modeling is also bidirectional. So what this means is when the FE model updates, unfortunately this animation is not showing up, if the FE model modifies, then automatically the CAD model also will update itself. Okay. Let me see if the animation can be shown here better. So now if you look at the animation at the bottom, all right, so the FE model gets modified, morphed, that is, and the moment you have modified the FE model, the underlying CAD also undergoes a morphing change, and the CAD also gets updated. All right. So in that respect, Meshworks is an associative modeler where it is bidirectionally associative. Meshworks is also an automated modeler wherein all your processes can be nicely automated in a highly visual environment with no need for script writing. Okay. So in multiple ways, Meshworks is going to help in cutting down your model building time and at the same time optimizing your product to meet your performance targets. So let me illustrate this further with some details. So far, is my audio, video, everything coming out all right, Hisham?
Yeah, everything is perfectly. We have a second machine on the side just to verify the audio setting and everything is coming out clear. Thank you.
Okay, all right, great. So one quick example with respect to how early stage concept design can be done. I'm showing an automotive example here. So if you want to create a member, it's as simple as clicking 2 endpoints and giving some dimensions, and the member is created. So if you want a curved member, which is going in as a stamped welded assembly, it has to overlap an existing member like this. Once again, in a matter of 2-3 minutes, such a member can be created. And now if you want to create a joint between this member and a target, for example, so you just show all the flange locations and this entire joint is automatically created. Okay. Likewise, a different kind of joint. Now let's say the joint needs to climb on top of the cross member. So the input is very minimal. Just point and click the source part, target part, and a joint is created. On an average, every one of these kind of members, joint creation, etc., the average time taken is about 5 minutes. And within that, you can create a new finite element model by sketching in a matter of few minutes. All right, and it nicely adheres to the surrounding contours of the surrounding assembly. Major customers in Europe or in North America, etc., or in Japan, they're all taking full advantage of this concept modeling capability, wherein with a minimal set of inputs like trajectories and cross sections, one can nicely create a new concept FE model. Either you follow the morphing route wherever possible, where you take advantage of an existing surrogate model, or you create a brand new model like what you see up on this animation here. Okay. In the interest of time, I'm just going to switch to another example, a success story, where one would want to convert a conventional vehicle to an electric vehicle architecture. All right. So what you see up on the screen is a conventional vehicle. The lower portion needs to be completely modified from an IC engine to accommodate a complete battery pack. All right. So, so the entire existing floor assembly is cleared out. All right. And then with the battery configuration given, using the concept tools that I showed a few minutes ago, the entire floor area was completely recreated using that. And what you see in this video is how all the new members are put back through the ConceptWorks tools, whether it's the floor area, dash area, cross member area. Every one of it is a FE model, and some of the regions get to be fairly complicated, like the members that is being displayed right now. All of this were sketched on the fly and created, and the entire underbody of a complex vehicle platform like this was done just in 2 days, 2.5 days. All right. So that is the speed with which one can generate a quick concept finite element model. I'm illustrating all this to give you an idea of how Meshworks will help you during the early concept stages of a new product development. And when it comes to the model itself is parametric. So what are the kinds of parameters one can have? So there is a wide range of parameters, starting all the way from gauge, shape, welding, adhesives, etc., and that applied across a wide variety of models. So if you are on the CAE side, it gets applied to structural models as well as CFD models. And at the same time, if you are also simultaneously addressing other aspects of modeling, like vehicle packaging or manufacturing, for instance, if you need to do a mold flow simulation or a stamping simulation or casting simulation, or for that matter, ergonomics, human factors, all these parameters that you see here on the x-axis can be effectively applied across multiple attribute models. It could be CAE models or non-CAE models like manufacturing models and human factors models, so that the parameters will allow you to make rapid design iterations, and at the same time, it will allow you to optimize. So what are the different kinds of parameters one can add? Let me get into some more detail. For example, if you take a stamped welded assembly, all these kind of depth parameters, or take a complicated region of a stamped welded assembly, this entire cross section is varied, and accordingly the surrounding members undergo the change, and it can be applied across multiple assemblies as well. All right, and the gauges of an entire assembly can be varied, or the material choice. If you have multiple material choices, it could be isotropic materials as well as composite materials. For composite materials, the number of layers of the composite, the material orientation, etc., all of that can be applied as parameters so that the material choices become the variable here. And then the connections, if you have bolted connections or spot weld assemblies, etc., or adhesives, the count of the welds or the count of the rivets, etc., that can be made as a parameter. Or if you have adhesives in your structure, the length of the adhesives, the location of the adhesives, all that can be parameterized. So in addition to all these categories of parameters, you can also put design features as parameters. And those parameters, we coined the term design enablers, and that would include a host of variables like introducing beads or dots or reinforcements with varying lengths, or different counts of the reinforcements, or a reinforcement length with variable cross section. Its length can be varied. Or if you have a plastic structure, the number of ribs in a plastic structure. If it's a seam welded structure, the number of skip welds or the width of the skip welds. If it is bulkheads, the number of bulkheads in the structure. So these kind of design features or design elements can all be nicely made as parameters. And you can make load path changes by completely changing the connection location of all your members. So overall, Meshworks becomes a very powerful parametric engine, wherein once you build a model in Meshworks, either at the early concept stage or at a detailed engineering phase, it is inherently parametric, which sets the stage for optimization. Now, on the meshing front, Meshworks has the ability to greatly cut down your model building time. So the models can be complicated tetrahedral models like this, with a high degree of control of the layers of tetra elements through the thickness, or it could be sheet metal assemblies, balancing the element size with the feature capturing, or it could be plastic structures with a lot of mid-plane meshing with variable wall thickness assignment, these kind of plastic structures, or it could be hexahedral modeling, complicated geometries. You want to create a hexahedral mesh in the shortest time possible. All that is possible in Meshworks. If you are solving a CFD problem, automatic extraction of the wetted surfaces, or if you are doing a conjugate heat transfer modeling, then doing the CAD stitching, all that can be very effectively done within Meshworks. All the connections, whether it is spot welds, seam welds, bolt connections, contacts, is all comprehensively addressed within Meshworks, and it can do it very fast. And it can go down to the detail. If you are modeling the entire joint, seam weld joint, with the weldment captured as hexahedral elements, and at the same time you want to model the heat affected zone, for instance, then we have very powerful tools which can automatically generate the heat affected zone in a welded assembly. So whether it's the breadth of functionality for modeling or the depth of functionality, like this example, Meshworks comprehensively covers all different scenarios. So we believe many of your modeling scenarios can be addressed quite effectively with our capability. And Meshworks also has the ability to, on the post-processing side, nicely take your results, like an abacus result, automatically extract the hotspots across multiple load cases, ignoring spurious results in rigid element regions or contact regions and whatnot, and gives you a nice summary. It robotically searches through the entire assembly and gives you a nice summary. And not only does it provide the entire summary of all the hotspots in the different components in your assembly, it nicely unionizes all those hotspots in one single model. Then you can, on the fly, click on any one of those locations and say parameterize it. If there is a high stress, change the fillet radius, and automatically the finite element model updates so that you can set the stage for the next design iteration. So these are all the key capabilities of Mesh Flux. There's one more slide I want to quickly touch on before I turn it over to my colleagues for some live demos. If you're doing a non-parametric topology optimization, Mesh Flux allows you to, number one, create a minimalistic design by allowing you to defeature and to reduce the wall thickness. This is the lightest design possible. All right. Then with that as step one, Mesh Flux allows you to create quick design space around the model. And then you run topology optimization like tools like using Tosca, or OptiStruct, etc. You create the topology results, and from that results, converting them into manufacturable FE models, manufacturable designs and the corresponding FE models. So Mesh Flux can effectively take your entire workflow for topology optimization and automate that to get you the results very, very fast. And with the parametric route, if you choose to optimize using the parametric CAE models, then Mesh Flux can take your running Abacus models and CFD models, etc., and using the design variables, it can nicely automatically create the parameters. And then through a tool like EyeSight, you can generate a design of experiments matrix, and then you can get all your runnable analysis models. If you have 10 designs, 20 designs, etc., it can generate that many solver models. You can run them, extract all your output responses like a fatigue safety factor or stress results and so on. And right there, you can pick up a better design than where you started off with. Or you can bring the input-output table back to EyeSight, for example, create a response surface, set up objectives and constraints, and get an optimized design. So in the last 5 years alone, we have participated in over 700 to 800 optimization exercises, small and big. These optimization processes that I showed in this slide and in the previous slide have been thoroughly vetted, and many customers are taking full advantage of this optimization process. So with that, I'm going to turn it over to Sridhar so that we can start showing some live demos. So Hisham, if you can make Sridhar the presenter, we will walk through some demos.
Yeah, done.
Okay.
Sure. Yeah, we can see your screen perfect. Yeah, go ahead.
Hi all, my name is Sridhar, and now I'm going to demonstrate you the tetra meshing for a cast component. So on my screen you could see a mount bracket. So it's in a single component. I'm going to demonstrate your tool like where you can quickly mesh it and automatically it becomes parametric. So I'm going to use interactive batch measure process. The process is pretty simple. A user have to select the component, and once we select the component, we have to specify the mesh template. So I'm going to use an existing template. So here we have wide variety of templates which are inbuilt. A user can use it, or you can modify accordingly. So I'm going to use a 3 mm maximum fillet capturing template. Just say execute. While it's running, I'll also show you like what the template has and what Meshworks is doing using the template which we are specifying. So I'm going to another window to explain you the template. So here in Meshworks, we have a mesh control panel where you could specify all the general meshing parameters like mesh type, general meshing parameters like element length, minimum, maximum element length. And along with that, we also have an advanced options like a user can specify the feature identifying parameters. Like a user, this is a template which I used for the demo. So if you see here, a user can specify the min and max diameter of the tubes, and you can specify the element length or number of elements. So like this, we can also specify the fillets for fillets. And by clicking on add button, a user can add multiple steps and based on the region. And likewise, you can also capture holes, fillet lines. Not just the feature identification part, you can also specify the mesh process control parameters. So right now it is a tetra, so I'm going with a tetra auto meshing control parameter. And also quality control parameters where a user can specify based on the requirement. And as we are going with the tetra mesh, a user have a control to generate a tetra based on the requirement. Like if a user want to go with a layered method, as Radha mentioned in an earlier slide, you can specify the number of layers and save the template whenever you want, so that a user can save it, and for ongoing projects you can use it as a reference. So this is what the mesh template has. Now I'll go back to the previous window to see like the meshing has completed. If you see the status, it says completed. I'll just say return. So before going into the meshing part, I'll just show you the CAD part. So the initial CAD which I selected was one single component, but after the meshing, Meshworks applied all the feature parameters onto your CAD, and it have organized the parameters onto your CAD model. So if you see like it have organized all the fillets into different PIDs, all your tubes into different PIDs, and along with that, you also see some small sliver surfaces on the CAD. And if Meshworks automatically defeatures this kind of small features to make your mesh look good without compromising the quality. So I'm going to on the mesh view, and I'll keep the CAD in a wireframe so that you could see like all the sliver surfaces have been automatically defeatured.
One point I would like to add, essentially we are saying zero CAD cleanup. So you don't have to worry about any manual tinkering around. All you do as a user is set up the template, and that too it's a one-time setting. So if you have a durability problem, you may have already settled down for a certain element size along the fillets, non-fillet regions, etc. So you set up the template, which itself is only a 5-minute job, even to set up a template the first time. All right. So after that, you point the template to the CAD, and then the tool almost runs like in a batch mode, and it does all the washer circle insertion and fillet region identification and CAD cleanup, which is identifying all the sliver surfaces, etc. And it saves the trouble for you, in doing all the manual effort. All right. And we have compared our meshing process quite extensively with other competing tools, and large OEMs like a Ford or GM or Toyota, they've all benchmarked quite extensively, and they have selected Meshworks for this kind of advanced modeling. Now that you have seen, you've had a glimpse of this, now we will talk about auto parameterization. Go ahead, Darshik.
So now I'm going to show you the auto parameterization part of the meshing. So as we discussed earlier, like once the meshing is done, the model becomes parametric. So we have already inbuilt some most used parameters into the software. So if you see, like I'm going to quickly change the fillet radius. Suppose like you have any hotspot on your model on this fillet region, you can quickly pick the surface, and you can specify the value, which is nothing but the min and max range. So I'm going to specify -20 and 20 as a percentage. and just say execute.
So this is a chain of fillets. So each fillet may have a different radius. So the -20 to +20% that we are entering in here is a percentage change with respect to the original fillet radius at each location.
So now the parameter has been created, and just to heads up to you, like if you see like on the top right corner, it also flashes the existing radius of the fillet on both either sides. Now I'm going to preview the parameters, review, link it.
So you can zoom in a little bit more. So now we are going to review the parameter to show how interactively you can control the fillet radius change. Now you can see the fillet radius being reduced, and now we are pushing the slider to the other end. You can see the fillet radius on the fly getting increased. Okay. So this is how simple it is with respect to introducing a parameter. It is as simple as you clicking on a set of surfaces and saying change the range, the radius range by this much. Okay. So go ahead, show the next one.
So likewise, like suppose like I want to increase the height of the rib so that my stiffness will improve. So I'm going to select a couple of surfaces on my fillet top surface, and I'll just say specify the min and max value and say execute, and in no time Meshworks create the parameter. So if you see, the process is very simple. So a user doesn't have to have expertise in handling the tool, because the steps are very easy. So now again, if you see, it have specified the existing position in XYZ coordinates, and I'll just say review, wall height. So in no time you can see like how quickly you can change the height of the rib.
So this is the whole idea of Meshworks being a parametric CAE modeler. The moment you mesh it, it becomes inherently parametric. In the interest of time, we are going to go to the next demo. Likewise, just like parameters like rib height change or fillet radius, there is also wall thickness changes, etc. In a typical exercise, you include all of that so that you can target a light weighting of the components as well. So now we will move on to the next demo. So we will quickly show you yet another model. Yeah, this is a fairly complicated entire structure. For a moment, let's go ahead and turn off the mesh lines and and then zoom out. So this is a complete platform, as you can see, for a heavy equipment. All right. So the customer had several wells in this model. Literally 2,000 wells were in this model. All right, at different well locations and whatnot. So you can now put the mesh back on. All the green elements, etc., or the weld elements where the fabricated structure has been welded at every location. All right. And now we will zoom out and show you different regions of the model. You can see what kind of a quality mesh that Meshworks can produce. Starting point is the 3D CAD data of all these sheet metal components, and then the customer's requirement as the meshing criteria or requirement, and then of course 2,000 wells. Meshworks did this entire job within a time frame which was only 1/3 the time that it was taking them with other competing tools. All right. So there was almost like a 2/3 time saving in building the entire model and automatically welding it. All right. So good quality model and at the same time automatic welding is the main takeaway here. So we will switch to one more demo. If you have plastics models, for example, the mid-plane meshing, etc., is a fairly challenging task. So now we will show a quick demo as to how this could be simply automated. All right. Go ahead, Sridhar. You can show this.
Yeah. I'm going to demonstrate the plastic meshing. So I'm going to use the auto mid-plane option here. So again, the process is pretty simple. A user have to select the component, and you have to specify the advanced input, like specifying the element length, min max values, and just say execute. So in no time, Meshworks automatically feeds in all the meshing parameters as we saw in the earlier tetra meshing demo. Likewise, it takes in all the feature parameters and it will apply onto the CAD. And not just apply. The thing is, like if you see in any other tool, we have to create the mid surface for the plastic meshing. But the good advantage of this tool is, like, we don't have to work on the mid plane because Meshworks automatically detects the mid plane. It will create the final mesh without creating any surface.
So give it another minute or so. It will complete the meshing. So the entire process of the meshing and then the subsequent thickness assignment based on the draft angle, that is also a fast, easy process within Meshworks. So components big and small, which are heavily ribbed, thin-walled components like plastic parts or thin-walled castings, etc., can have a great advantage with respect to this modeling. So it's already done. So now we will show you the results. All right. So you can see with no intervention from the user, it nicely connects, extracts, stitches, and connects the entire model together. All right. So now we are going to switch gears. In the interest of time, I will turn it over to Paresh. So you can make Paresh the presenter, Hisham. Yeah.
Can you?
Yeah, click on that, show screen. Yeah.
Yeah, okay.
Okay, Hisham, are you making Paresh the presenter? Can you confirm?
He's already presenter. Yeah.
Oh, great.
Yeah.
Okay.
Yeah, we can see his screen. Perfect.
Okay. All right. So now we are going to show a quick Hexa machine demo. Over to you, Paresh.
So here we see we have a bumper foam model. As we can see here, this is a CAD model, and we have created, by using the same technique which Sridhar showed, we have created a mid surface. So this is a new technique where very fast we can create a hex mesh from a very complicated kind of a structure. As we can see here, there are a lot of fillets. There are some features which we need to capture in hexa meshing. So manual time, it takes a lot of time, but here there are some prerequisites. The prerequisite is, like, we have to create a mid surface mesh, as we can see here. So once we have the mid surface mesh, we have a very nice tool, that is Hexa from Shell. So user just has to select the elements, give a minimum thickness of the wall, and simply say execute. So when a user say execute, it will very nicely go ahead and generate a T-junction offset hex mesh. So if I click on reset and click on execute again, as you can see here, so this is the pre-step, or this is the step one, which I would say, that is to create a core mesh. So as we can see here that as the CAD is having some draft angle, but our mesh isn't straight. So this is nothing but our core mesh. Now once we have the core mesh, user just has to export this core mesh outside, and then he has to mesh the CAD. Okay, so we are meshing the CAD just to get the outer geometry. So we have a tool in Hex Mesh where we just have to select the outer geometry so as to capture all the fillets and small features, and it is independent of the mesh. It might be a mixed mesh, it might be tria or quad mesh. Once we select the outer geometry, then we have to specify the element size. Now we have to import the same core mesh which we just created. So I have exported out beforehand, and I'll show you the same core mesh which I just exported. So this is the same core mesh, and I have to select cavity and simply say hex mesh. So within less time, a hex mesh has been created with a very nice quality, as you can see here.
So to summarize the steps again, you're creating a brick layer inside the geometry from step 1, and using that brick layer, now in this auto hex mesh, you are doing a plastering, outside plastering, to adhere to the true CAD geometry. Okay, and both steps are very fast steps. So likewise, Meshworks has got the widest variety of hex meshing tools. If you can quickly flash the panel, we are the industry best when it comes to the hex meshing. You can see we have literally about 25 odd functions just devoted only for hexahedral modeling, all the way from very complicated geometries to swept geometries, etc. It could be civil structures, it could be heavy industry equipment like boiler structures, nuclear equipment structures, piping. No matter what kind of model you're looking at, Meshworks has got some very powerful tools to greatly reduce the time that goes into hexahedral modeling. Now, with that having said, we will quickly go into a welding demo. Now we are switching gears and showing some connections demos. Go ahead, Paresh.
So here we see there is a tube and a bracket, and as let's say we have to create a seam welding right here, which is a hexa seam welding. Now we have a lot of options to select the path, where we have to select. So I'll be going by 1D element, as I have created one 1D line. So I will select my 1D line. I have to select my master components and my slave components. It is nothing but the connecting components. Then I have to give the solid weldment inputs. It's nothing but the weld width, how much weld width I want, element size, number of layers along the weld. And if you want a hexa mesh, I just have to check on mixed mesh. Simply say accept. Before accepting, we have also wide varieties of profile. First, we will see how the flat profile is. So once we say accept, then we have weldment type as weld, and then align type is merge nodes, coincident nodes with contacts, non-coincident nodes with contacts. So I will go with the merge nodes and simply say preview. So as we can see here, it will very nicely create a flat profile and also a hexa mesh, hexa seam weld right here. So I will quickly click on reset and show you the other profiles. I'll go to concave. Now you can see here how nicely a concave seam weld has been created. Now I will show you the convex. This is nothing but just a preview, but when we say realize, now I'll click on realize. So as I click on realize, it will very nicely go ahead and do the node-to-node connection between the weld and the connecting components very nicely.
So depending on how you are modeling in Abacus, for example, node-to-node matched, node-to-node connected, common nodes, or with a contact between the weldment and the surrounding, Meshworks facilitates all of that.
So as we can see here, there is very nicely, the seam weld has been connected to the connecting components, as we can see here. And not only here, it is going across the thickness, right here and here.
So as you can realize, the tool does everything automatically. This is a fairly challenging problem, as we all know, being in this industry. We have taken the pain out of this whole process. Now we will show one more quick welding demo with a cross section that can be sketched by yourself. Let's say if you have a multi-pass weld, and in the case of a multi-pass weld, you need to really define the cross-sectional shape yourself. All right. So that is the next demo we are going to show.
So now I will be using defined cross-section, but instead of realizing by a 1D line, I will use it by nodes. So you can define your path, the starting point and the end point. Then similar process, you have to define your connecting components. Here we just have to check on mixed mesh, as we want a nice chord mesh to be created. So as we click on define cross section, it nicely takes the cross section and it will show you the green point. That is nothing but the starting point of our weld. So here a user can nicely go ahead and sketch it as per his requirement. So let's say I have created a seam weld in this profile. User can go ahead and create as per his convenience. I can increase the feeding point here so as to get a very nice chord mesh. Okay, click on accept, and now I'll click on preview so as to see the weld. Now I will quickly click on realize, so it will very nicely go ahead and do node-to-node connection again with the connecting components.
And while it is doing, I want to add a point. In all this, in this particular demo, you saw the weld line itself is being defined on the fly. You as a user can specify one end to another end, etc., and you can generate the welding process that way. Alternately, you could also directly import weld lines. If your CAD geometry itself has weld lines, then it can go ahead and treat that as your weld information. And we have automated tools which can nicely identify within a proximity to those weld lines which are the connecting parts, and you can create the weld connectors. And likewise, if it is a 3D geometry of a weld that you have as a 3D solid part for the weldment, that can also be recognized and it can weld. So now, in the interest of time, we are going to march ahead and show one more bolt connection option. So if your assembly is a connected bolt set of parts, all right. So there are different ways to connect them with bolts, solid bolts versus beam-based connection. So this demo will illustrate that.
So now, as we can see here, there are 3 components, and a user can select all 3 components. But with respect to the time, I will only select the 2 components. And now we have like fastener type, whether it is screw type, through bolt, or multi-thread. So here we have a screw type. Then next is like connection, how we want the connection. So the bolt connection, centroid, unilink, hybrid, this all are 1D bolts, 1D link. And then if you go for a solid connection, it creates a 3D solid bolt connection. So let's say I go for a bolt connection for now. I give a diameter range. Before that, I give my shank part. So this would be my shank part, and I will say detect cavity. So software will very nicely go ahead and identify all the holes onto in these 2 components, and it will only highlight the holes which are connecting to each other.
Go ahead and turn off the solids for a second. So you can see it nicely detects, just like CAD feature recognition, it has Meshworks has the ability to detect FE features as well.
So once the holes have been detected, user just has to give a material
For the bolt.
And simply click on preview. So as we click on preview, I will turn off my 3D and put my 2D into wireframe mode so that we can see a very nice bolt connection between the two components.
It's a combination of beam elements representing the diameter of the shank and rigid elements connecting to the surrounding. So we have only a few more minutes with respect to our demos. So now we will switch gears. Instead of showing the solid bolts, I think they get the general idea. Let's quickly show the parametric models. At least one or two parametric models that we should show. One parametric model, I think, Paresh, since you are already the presenter, you can show the ONG application. You had a parametric model for one of the oil and gas projects that we worked on. So go ahead and show the parameters on that, and I'll start describing what it is. This is the riser guard platform, riser guard for a platform, and this model has several loads, and we had to optimize this to reduce the displacements and stresses. So go ahead and show the parameters, what kind of parameters that we worked on. Can you zoom in closer so that we'll be able to see it clearer? Yeah.
So the first one is width. So let's say if we have to increase the width right here, so we have created some parameters. I'll quickly show you. So as you can see here, how nicely or how quickly I can just increase the width.
Of course, here just as an illustration, we can put constraints as to preserving the holes, or other features while doing the parameter change. All right.
Then the next is lug hole height. So if we have to increase the height, so we can very nicely go ahead and increase it. Then we have the rib location. So let's say if we have to change the rib location, as we can see here. Then we have the component length. Let's say we have to increase the length of the component, as you can see here. If you have to go for a support height,
so you get the general idea. So every feature in your structure can be parametrized, and this is a stamped welded assembly. Now we are going to show another quick demo. If you Hisham, if you can make Sridhar the presenter, that'll be good.
Yeah, sure. 1 second. There you go.
So we are going to show a couple of aerospace-centric applications. This is the impeller of a turbo machinery. All right. It could be typical. It could be related to aircraft engine and blade structures. So here, the profile change of the blade is one such parameter, and this is at another parameter. Yeah. Now you can explain the parameter. This is the thickness of the blades.
Height of the blade, the smaller blade.
And this is the height. So alternating blades are of different height in this case. This is a profile change of the blade.
and this is thickness of all the blades at a time.
So obviously, when we are setting up this analysis, all the blades should have the same uniform movement. All right. So that is the illustration here, and the height you have to set up a different view. Correct? Yeah. Yeah. So you can see how the height of the blade is modified. So such complex parameters can be applied with ease. One more example. This is the box structure inside a wing. We will turn off the top one, and you can see all the ribs inside the model. And there are some 1D elements also, I believe, in this model.
Yes, sir.
Turn on those are the stringers that you see in the model. All right. So if you're in the early stages of the modeling, where you want to position the ribs at a different location, either all the ribs or an individual rib, you want to relocate to a different location. Can you show a side view showing the taper? Yeah, go up a little bit. So now go upward a little bit. Rotate up, rotate. Yeah, there you go. And now move the rib. So one of the interesting things to notice is obviously the box wing structure is tapered. Now, as the rib is moving, the rib is also reducing in height. Okay, such interesting relationships can all be nicely put when we parametrize. All right, and the shape of the ribs where the stringers come and sit is the parameter that is shown here. And the last one is the stringer position, with which you can relocate the stringers to different locations. All right. So this is also in the early stages of the product development, when you have access to a lot of these variables. A lot of our aerospace customers like this ability to play around with the locations and shapes, and even the count, the number of stringers, number of ribs, number of bulkheads, etc. All of this can be applied as parameters. Yeah. So overall, what you see here is the ability to take a wide variety of problems, and whether the component is sheet metal assembly or castings, or bolted assemblies, welded assemblies, Meshworks has the ability to parametrize all of that. For example, the welded assemblies, we are having the ability to control the length and width of the weldment, or the cross-sectional parameters of the weldment, or the wall thickness of the entire piping. So, and the nature of the models could be shell models, tetrahedral models, hexahedral models, doesn't matter. Regardless of all that, you can, number one, model it or mesh it very fast, and number two, parametrize it, and number three, you can optimize it. Okay, so this way you can really get to your optimum solution very, very fast. So Hisham, now if you can make me the presenter, I'll make just one concluding slide, and after that we can open it up for any questions.
Yeah, sure. 1 second.
So all the turbo machinery also finds its application in the oil and gas industry. That's what we were attempting to say earlier. Now coming back to a few points I want to conclude with. Using Meshworks, with this kind of an optimization, I'll just flash a quick example. You can take a very complex problem like this with several different load cases, all right? A whole bunch of durability load cases, noise and vibration load cases, and manufacturing load cases. You can, and this is all driven by multiple models. Noise and vibration model is different from durability, which is different from manufacturing, but the parameters that are applied is common, all right? Some are castings related parameters, some are stamping related, all right? So you can apply the parameters across multiple types of components, even on the same assembly. And then you run your optimization, the design of experiment space optimization, meeting all the different load case criteria and still be able to get a tremendous weight saving. This is just one of the 700 odd examples that I was talking about. So an axle 5.5 kilogram weight reduction across several load cases, through this kind of an approach is the value that you can expect at the end of the day. So with that, I will stop here. So Meshworks is a parametric modeler, associative modeler, automated modeler, and it's an integrated modeler. Now we'll be very glad to answer any questions that you may have.
Well, thanks a lot, Radha, John, and the team for the live demos, the detailed presentations. It was amazing to see a lot of Meshworks capabilities. I have a few questions here. Some of them are repetitive. So one of them is basically, how does Meshworks compare to the competition? So mainly HyperMesh. How do you guys see yourself comparing the two?
Yeah, Meshworks has been benchmarked extensively against HyperMesh and SimLab, for example. Very large customers like Mercedes-Benz, or a Ford, or a Toyota, they've benchmarked Meshworks extensively, and using just one model, literally talking about 20, 25 models, all right? And the conclusion is that overall, Meshworks gives them about 40 to 50% time saving during the model building process, number one. Then when it comes to the parametrization, Meshworks has the most comprehensive parametrization. This is a Toyota speaking, for example, all right? If you look at the parametrization at the bottom of the screen, we have literally about 30 odd parameter categories, all right, all the way from a shape to a welding, whereas HyperMesh has got only 10% of this parametrization capability, all right? And then, of course, the other key elements like the associative modeling and so on, where in a production basis, as designs keep evolving, you want to keep updating the models. There also, a lot of these competitive benchmarks have come back saying the model updates, quick model updates, there is a tremendous time saving, even much more than 50% time saving in such cases compared to HyperMesh and SimLab. And one of the things our customers like very much is that all under one roof. So that also came as a pleasant surprise to us. We ourselves did not take note of it initially. What they said was for different kinds of modeling. So for example, if it is tetrahedral modeling, they have to use SimLab. If it is shell element modeling, they have to use ANSA. If it is connection, they have to use HyperMesh. So the engineer needs to be trained in multiple tools, whereas Meshworks had everything under one roof. All right. Okay. So these are all the key benchmark outcome that we learned from many of our significant customers as compared to the competition. Yeah.
Okay, perfect. I guess we have like a few minutes before we should probably wrap up by now, because I need to handle the ball to Trullo team. So again, one more time, thank you so much, Radha. Thank you, John. Thanks, Paresh, and the engineers team. We appreciate your effort and the time you put together for these live demos. And of course, we'll follow up later with some other specific customers that they have like some specific inquiries. Thank you so much again, guys. Thanks.
Sure. Thanks a lot, Hisham. Thanks a lot for all the participants. We really appreciate your patience and attention. And of course, let us know. Our engineers are on standby. After the presentations are over, if anyone wants to see any further demos, we are on call. Yeah.
Yeah, for sure. Thank you so much. Thanks a lot again.
Thank you.
So here we're gonna switch gears to talk about the different topic here, which is Know Your Loads with Tim Hunter from Wolfstar Technologies. He'll be presenting an extensive presentation of True Load. So Tim, the ground is yours.
Okay. Thank you, Hisham. So just wanted to let me just get my presentation set up here. So thank you. That was a fascinating presentation by Meshworks. I was very impressed with all the welding. Being a guy who used to be at Harley Davidson working on frames and welds, that just looked like a lifesaver. So thank you all for joining us today to learn about True Load and load calculation technologies, load reconstruction. The little animation you see on the screen here is a project we've done on a Razor scooter, a nice little example project we've done, and we're going to do this live today. So we'll get into that shortly, but let me get right into the presentation. So a little bit about Wolfstar Technologies. We were founded back in 2010 by me, Tim Hunter, and I was before founding Wolfstar Technologies, I was at Harley Davidson for 22 years. I was chief engineer of vehicle structures, and I've dealt with practically every aspect of product development. I'm sure that many of you are dealing with. So I've been through it all. I understand what it takes to develop products, and I really think we've got a fantastic tool here with True Load to help you understand your loading so you can do better product development. We've got great development partners in Dassault Systems, ANSYS, MSC, and CE-Tron is a tool that we're using for our 3D visualization environments. So this is just the elevator speech here. So really only with True Load can you use FEA and test to understand your product loading. We're going to turn your parts into load transducers and leverage your FEA model to do that. So this is what we're doing. So just a snapshot from our website here. This is a snapshot of our customers, and actually this is out of date, but the customers highlighted in green, these are customers who are using the True Load technology either as direct customers or we've done consulting jobs for them to help them understand the loading of their projects. And you can see that we've got great customers in a very wide variety of platforms here. So real briefly here, the products from Wolfstar Technologies, True Load is our flagship product. Basically, True Load turns components into load transducers. We do this by having the user place unit loads on their FEA model. We take a look at all those unit loads, come up with idealized strain gauge locations, extract a correlation matrix. We have the users place the strain gauges on the physical parts and collect the strains on the physical parts. Once you've collected those physical strains, we'll take those measured strains, multiply them by that correlation matrix to back calculate the loads. We're basically making a load transducer out of your part. Another product we've got is called True QSE. True QSE stands for quasi-static events. And basically this will take individual result sets from your FEA model and let you linearly superimpose them by user-defined functions. That by itself is great, but what's happening with True Load is we're getting time histories of loading mapped back to individual result sets of your FEA model, and True QSE becomes a tool that allows you to visualize and explore your model. So you can create XY plots anywhere in your model, create operating deflection shapes. It becomes a very important part of post-processing your model. And True QSE is so important for understanding your results. We bundled True QSE in with True Load, so when you buy True Load, you get True QSE automatically. And a third product we've got is called True LDE. LDE stands for Linear Dynamic Events. And basically, this is an FEA-based post-processor for all of your linear dynamic solutions, time domain, frequency domain, and PSD domain. Most post-processors aren't really tuned towards these types of analyses, and this is a post-processor that's really, this is what it deals with, is these types of solutions. So it's really makes post-processing your complex time and frequency domain analyses very, very efficient. So these are all the products from All-Star Technologies, and all of our products are so concerned about getting the loads correct that we basically give you tools to automatically send those loads out to your FEA-based fatigue softwares. Because loading is the hardest part about doing FEA-based fatigue. So we've got direct interfaces to tools like FE-Safe, so we can create a deck for you for FE-Safe, and you can run your fatigue analyses very, very efficiently and very quickly. And it basically ends up building the FEA-based fatigue into just a natural part of your workflow, because to get there, it's just a button push from our tools. You don't need to have FEA-based fatigue to use our tools, but if you've got it, we make using that easier. So the whole motivation behind TrueLoad is quite simply, what's the load? If you're a design engineer or an analyst that's got developed parts for this motorcycle, and you're responsible for making them function and be durable, but the loading on the motorcycle is crazy nonlinear. You can't measure this load, you can't simulate this load, but you as the design engineer, you as the analyst are responsible for designing parts that are functional and durable. What do? Well, we recognize the individual components of the motorcycle are basically responding linearly. So we'll target the swing arm, the frame, the crankcase, the handlebars, the gas tank, the fenders, the luggage systems. We'll put strain gauges on these subsystems and let these subsystems become their own load transducers to measure the operating loads on the structures. And then we'll use those loads then to back calculate the loads in the subsystems, and you can use those loads then to do design and optimization. This is a first to market solution. It's based on a technology called influence coefficients. Influence coefficients have been around for about 50 years. Problem with influence coefficients is that historically it's all been manual. Manually place the strain gauges, manually set up very expensive tests in the lab to do your unit loads, and then you get to the field with a bad correlation matrix, and the loading you'd get back would be no good. So the technique never caught on. And what we've done is we've taken all of that manual work and optimized it with scripting and the FEA model in order to get the best gauge locations and the best correlation matrices possible. So a little bit about, some historical concerns with doing analysis. Loading is the biggest unknown when you're doing an analysis. You can have a perfect CAD model, you can have a perfect mesh, you can have a perfect solver, you can have a perfect material model, but oftentimes when you go to throw that solve in for an analysis, you're making a guess at what the load is. You've done a back of the napkin load calculation, you could have a departmental standard, but at the end of the day, it's more or less a guess. And if you're guessing at your loads, you're basically guessing at your results. In the US, we've got this term called GIGO, garbage in, garbage out. And people try to get a better handle on this with using tools like these load transducers like you see on the screen here. And they're fine. These load transducers are just fine, but they're expensive. And every time you use them, you've got an expensive operation to modify your parts. So now you got to cut out material, you insert the load transducer. Now you've just modified the mass, you've modified the stiffness, you're measuring something, it may or may not be the actual loads. And then worse yet, you bring those loads back to the analyst and they're working on the as designed part. Now the analysis guy's got to rework his part to look like the test part to use the loads you just measured. It's not a great solution, but this is traditionally what people are forced to do. Another approach that people try to use are strain gauges. Typically what will happen is the analysts look at their FEA model, take a look at the stress and strain plots, come up with some strain gauge locations off the FEA model, might talk with their colleague, come up with some more. They might have 30 strain gauges, go off to the field, you collect time histories of strain data at these 30 strain gauge locations, and then you look at these strain plots and you look at your FEA model and you just scratch your head. The loading in the field is so complex versus the loading on your FEA model. And typically you'll pick 1 or 2 channels of data at 1 or 2 points in time. You'll work for days, if not weeks, to get a load case that just matches qualitatively. And you say, that's your design load. And then you use that for your design and iterations. And then the next time you get back to the field with hardware, you find that you've got the same problem or maybe even new problems, and you repeat the whole process. This is typical. I've done this in my past. I'm sure many of you have done this too. So what's wrong? Your company is getting great people, great FEA software. They're doing the right stuff by testing, and you're using tools like FE Safe to do fatigue analysis. So your company is making all of the right investments, but they're not getting the right answers. Well, what's going on? Well, the problem is you just got too many variables. You got gauge locations, you got load cases, and the quantity of data. So if you've got 30 strain gauges laid on your part, you go to the proving ground, you come back, you'll have a time history of maybe 500,000 data points. And the problem is at every point in time of those 500,000 data points, you've got a unique loading recipe. So now you've got to come up with 500,000 unique loading recipes. And that's just impossible to perform manually. And you're just kind of left in this no-win position. It's just a hard job. So the solution here is TrueLoad. TrueLoad's doing what's called in situ load measurement. In situ means in location load measurement. So we're going to turn your components into multi-channel load cells. We'll leverage the FEA model to work with the test data. We can work with any FEA. We've got really nice plugins for ANSYS Workbench, Navigate CAE. But at the end of the day, we'll get optimal strain gauges, and then those strain gauges will turn into strain correlated loading functions. Now that we've got these strain correlated loading functions, we can push those off to your fatigue tools. So this is really what we're all about. This is the solution we bring. So we've got customers in all these product segments. If your product is getting loading from the wind, sea, air, ground, from the customer, or even internal loads, we can help you understand the loading, back calculate those loads so you can use those loads for design and optimization. So this is a typical V diagram in product development. It's kind of a nice way to talk about the problem. You know, you start with a V diagram with the voice of the customer on the left-hand side. You go into product requirements and functional specs. Then you start getting into CAD and FEA design, going system, subsystem, and component design. So you're on the virtual side of the world. You're doing all this work. And then when you want to start making sure things are working out, you go physical testing side, looking at component, subsystem, system tests, and finally functional acceptance test. And then you launch a product. That's pretty much the V diagram. It's a great model for doing product development. And where TrueLoad fits in is that we're basically taking the data from the expensive testing side of the world, and we're bringing it back into the analytical virtual side of the world. So we can drive our analytical models with all this very expensive work we're doing on the physical side of things. So we're trying to bring that physical test data back into the virtual world so we can go through this iteration cycles fewer and fewer times, and so we can really optimize the design process and get to a very efficient design. So I'm going to go through the workflow for TrueLoad. The workflow really just starts off with an FEA model. This is just a typical FEA model, but rather than you coming in with a complex load case, I'm going to have you come in and set up a series of unit load cases on the model. So it'll be like 1 kilonewton in the X, 1 kilonewton in the Y, 1 kilonewton in the Z, maybe a pressure load, maybe a thermal load, maybe an inertial load. And the way to think about these unit load cases, that if you could mix them together, could you approximate the operating conditions on your component? So once you've got these unit loads solved, then we go into the pretest software. The pretest software looks at all of the strain results for all those unit load cases, comes up with the optimal strain gauge placement. Once we've got these optimal strain gauge placements, there's tools that allows you to reposition and reorient the gauges to make them easier for the test guys to lay. And then we'll store off a correlation matrix that relates the strain response of the gauges to each of the unit load cases in your FEA model. We'll store the correlation matrix off to disk. We'll take the gauge placement information. We'll bring that into this to the lab and place strain gauges on the physical part. And then we can just collect strain data. So we can collect strain data in the lab. We can collect it on the proving grounds. You can even collect it in your customer's hands. We just need time histories of strain data. Once you've collected the strain data, then we bring that back into the post-test software, and the post-test software is going to take the measured strain data, multiply it by the correlation matrix from pretest to generate for us time histories of loading functions. Now these are just loads. You could bring them back into your FEA model using manual means if you'd like, but what I highly recommend is you use the true QSC models that get generated automatically, which manage each of the unit load cases and the corresponding loading functions. It allows you to quickly probe the model for any response you want anywhere in the model, or generate operating deflection shapes. And then once you've got this strain correlated loading information, you can always bring the strain correlated loading information now into your fatigue-based softwares like FVSafe to drive your fatigue analysis. Because the hardest part about doing a fatigue analysis is getting the duty cycle right. And now we've just solved that with the strain correlated loading functions. So this looks a little bit complex, but really the first 4 blocks are you turning your part into a load transducer, and once you've got those loads, then you doing design and optimization once you've got the loads. So you might do the first 4 blocks once, and the bottom flow chart 20, 30 times as you optimize your part. So this is all based on linear systems and loads. So linear system is where loads are proportional displacements, displacements proportional strains, strains are proportional loads. It's a linear system. Now I fully realize everything in life is nonlinear, okay? But what we're doing is we're turning your part into a load transducer. So we're going to target nominal areas to place the strain gauges. So we'll stay away from welds, we'll stay away from bolted joints, we'll stay away from areas of contact. We're going to be in nice nominal areas where the strain response remains linear and proportional to the loading. The loading can be as nonlinear as anything. It can be sinusoidal, ramp loading, impact loading, that's okay. We just need the strain response to remain proportional and linear to the loading. So I can take this little diagram here and turn to a couple of equations. So the right-hand side, well, that's F equals Kx. So that's Hooke's law. So if your part is obeying Hooke's law, then the left-hand side of the triangle has got to be obeyed as well too, which is strain times the correlation matrix is equal to load. And we're going to calculate loads as being strains from test times the correlation matrix from FEA. So this is what we're doing. Earlier on, I said this is based on the science of influence coefficients. This is the governing equation for influence coefficients. So I'm going to go into a little bit deeper mathematics here on the next couple of slides here. So here we got strain times the correlation matrix is equal to load. And so in this example, I've got 3 unit load cases and 4 uniaxial strain gauges laid on my FEA model. So the columns of my strain matrix each represents a uniaxial strain gauge. And let me walk through this row by row here. So here if I turn load case number 1 on and load cases 2 and 3 off, and I measure the strain response at these 4 gauges and write that down. Okay, so I'm just going to write down the strain response at these 4 gauges. Now let's go into the next load case. So we turn load case number 2 on, load cases 1 and 3 off, and now at these same 4 strain gauges, I'm going to measure the strain response. Now the strain response here is going to be different for load case 2 because load case 2 is different than load case 1. So we're essentially getting a unique strain signature for each load case. So we get load case number 2's unique strain signature. And then we do it again for load case number 3. So we turn load case number 3 on, load cases 1 and 2 off, and we get load case number 3's unique strain signature. So now we've got 3 unique strain signatures, 3 unique load cases. We've got a well-behaved linear set of equations. We can solve this, okay? So let me talk about these unit load cases for a minute here. These unit load cases, they could be loads, they could be moments, they could be unit displacements, they could be pressures, they could be thermal loads, they could be inertial loads, they could even be mode shapes. So if you set up gauges based on mode shapes, Truly will directly calculate modal participation factors just from the strain gauges. It's an extremely powerful way to understand the dynamic loading of your structures. Okay, so the big unknown here. So the only thing I haven't talked about is C. So how do we find C? Well, if we think of the F matrix, if we call turning a load on a 1 and turning a load off a 0, that F matrix can become the identity matrix, and then I can do a pseudo inverse. So you take strain times C is equal to I, pre-multiply by strain transpose, pre-multiply by strain transpose, strain inverse, and you get C is equal to strain transpose, strain inverse, strain transpose, and that's what we pull out of the FEA model. So this is our correlation matrix that we're getting out of your FEA model. And then finally, we've got millions of places to lay strain gauges. So how do we know where the best ones are? So we look at our nice little equation here for C, and we see we've got this inverse. Inverses can be very poorly behaved. We want the best behaved inverse there is. So we recognize that the inverse of a matrix is defined by the cofactor of the matrix divided by the determinant. So the thing in the bottom, I don't want that to be 0, I want that to be maximum. So this is our objective function. We're going to maximize the determinant of strain transpose strain, and we do this with this Galil-Kiefer d-optimal search algorithm, which is extremely efficient for finding the gauges. So this is how it's done. So I'm going to go through the workflow real quick here. So this is a headlamp on a motorcycle. This analyst says, hey, this is getting all sorts of vibration from the front suspension and from the engine vibrations. The analyst is going to treat this as a base excitation problem. So he chooses to set up his FEA model this way. He's going to restrain the bolt holes to ground, and he's going to put 10 G's X, 10 G's Y, and 10 G's Z as his unit loads of the FEA model. He solves it, goes into pretest software. The pretest software loads up his 3 unit load cases. Then he's going to select a subset of the model for placing strain gauges. So he's going to pick elements in the middle of the headlamp bucket and in the middle of the legs. He's going to stay away from areas of high stress concentrations, like the boundary conditions and where he's got RBEs hooking parts together, or nice nominal areas on the part. So he's got these as candidate elements for this for finding strain gauges. Tells TrueLoad he wants 6 strain gauges, and TrueLoad goes off and finds the strain gauges and draws them up as lines showing the position and orientation of each gauge. So once he's happy with those gauges, then he instruments it up and gets a bunch of measured strain data. And now the whole idea is to take this measured strain data and turn this into calculated loads. And he's going to do that with post-test. Post-test is going to bring in the file from pre-test, bring in the strain data from test, and he pushes the button to calculate the loads. It's really that simple. But there's lots of things here where we can map up channels and plot data. But really, at the end of the day, we're just bringing the correlation matrix in from pre-test, strain data from test, and pushing the button here to calculate loads. And what's happening here is we're going to take the measured strain data, multiply it by that correlation matrix to generate the loads. And now that we've got the loads, the post-test software is going to generate an HTML report for us that's going to show the measured strain data plotted against the simulated strain data. And we want to look for a nice 45-degree line to make sure we're getting one-to-one correlation in our strain response to the FEA model versus the real world. And then post-test is also going to generate for us a true QSE file, and this true QSE file is going to have our unit load cases and the corresponding loads that were calculated by post-test, and then we can probe any node or element we want for any data component of XY plots we want. We can generate an operating deflection shape, or even go off and do fatigue analysis with tools like FESafe. So now we've got a way to go in and fully query our model from our tests. Now this is great. We get to see what our part did, but if we want to get into the redesign mode now all we have to do is go back to the FEA model and we can make whatever changes we want. We can poke holes in it, thicken things up, change connections, and the only requirement I'm going to put on you is you just solve it with the same 3 unit load cases we start with. So now the solves are extremely simple. They're just unit load case solves, and we bring this new database back into our True QSE software, and we have the True QSE software point to the new FEA results database, and then all the results will be linearly superimposed properly by our loading functions, and we can see the response based on our new geometry changes. So this gives us an extremely efficient way to do design iterations on the structure. Okay, I've got a couple of customer examples here. This first one is from Honda. Honda is using this on all sorts of things, but this example here is a steel tube for oil passages on one of their engines, and they were having issues with some fatigue cracks happening on this, and the loading on this is extremely complex. They've got pressure loading, they've got thermal loading, and they've got physical, mechanical loading going on in this. So there were all sorts of loads coming into this structure, and they needed to have a way to understand the loading so they could go in and design and optimize their result. And what you can see here is some of the results here. They're showing results from the true load calculations of showing on the horizontal axis, you got measured strain, and on the vertical axis, you got simulated strain coming back from true load, showing how well our loading reproduces what they had on their engine. And they could use those loads to redesign and optimize their part. So they were able to turn this around in record time to fix this problem. This is a nice problem from another customer of ours, Aaron's. They make these high-end zero turning radius lawnmowers. And this engine deck that you see here, it sits underneath the seat here of the engine, and the engine and transmission sit on this. This engine deck was working just fine for them, but their transmission supplier needed them to provide airflow so it could get airflow to the transmission. So they talked to us to see if we could help them out. And then working with the design engineers there, we decided to treat this as a base excitation problem, because basically the whole vehicle is going across the proving ground, bumping along, and so it's basically a bunch of rigid body motion going in. So we model the engine and transmission as lump mass, tied it into the engine deck here, and we put 10 Gs, X, Y, and Z. So you can see our unit load cases. And then TrueLoad came up with 8 strain gauge locations that we had to put on here. So we had these 8 strain gauges we laid on the structure, and then they went off and collected the strain data. And so this next slide here, what you see on the top left is all 8 strain gauges going across their proving grounds. And then we use those strain gauges to calculate the loads, and then we go back into the FEA model and pull out simulated strains at the gauges. And there's actually blue curves on that top left curve. They're line on line, so you can't see the blue curves. And down below, we've got a cross plot of measured strain versus simulated strain, showing the type of correlation that we can get with TrueLoad. And now that we've got the loads, we can then generate an operating deflection shape, which you see up there. And now the beauty about this project was Aaron's has got really great design methodologies, and they actually had a design guide for these engine decks. And they had one of their engineers come up with their first design before we got there, and they had it prototyped and on test. And they were so proud of this thing, they wanted to show it to us down to their shaker test. This product's supposed to go 10,000 hours on their shaker test. We got down there, the part had failed about an hour before we got down to their shaker test, and it failed in 1,200 hours. And I said, perfect, give me that thing, let me see what it does. And so that you can see the stresses and strains our loads are putting into this engine deck. And then working with the design team, we came up with a different hole pattern. So our first design iteration then was some larger holes, and we actually had 2 layers of sheet metal riveted together. While this was working out great, the manufacturing guys hated it, so we'd go back to down to 1 layer, and then we iterated on sheet metal thickness over the next couple of days to come up with the final design. So let me show you the durability results here. So this is all done with FE Safe. So you see their fatigue curve here. The yellow is indicating their 10,000 hours, which was their goal. So we want to look for yellow, green, and blue on these plots. Their baseline was fine. There's some red because they are E's, but basically their baseline design was fine. And then here's the design that failed in the lab. So this failed in the lab in 1,200 hours, and in FE Safe it was predicting 1,000 hours. This is perfect correlation. So then with that additional confidence, we ran through and we did fatigue analysis on all of our designs. And you can see by the end of the week, we had a design with the airflow that they needed, and actually with better durability than they started off with. So this is what you can do when you understand the loads. And when you talk to the engineers at Aaron's, they said if they had done this project without TrueLoad, each time they did an iteration, it would have been $30,000. It would have been about 6 weeks to procure, and we're guessing at the loads each step of the way. So we did 5 iterations, so that's $150,000 in 30 weeks. And with TrueLoad, we did it all in 8 days and under $1,000. So that's the order of magnitude that you can get. If you understand your loads, you can make the right design decisions and get the job done quickly and properly. And I've got one more application here before we get into a live demonstration. So this is a bulldozer from C&H. This is actually pretty old now. See, when I came and talked to this bulldozer, and when they told me that the analysis guys couldn't match anything in the lab couldn't match anything in the field, and everybody kind of thought the other guy didn't know how to do their job. And so we kind of went in and started working on this project. And what we did is we put XYZ loads in the front of the blade. We had a load here on this hydraulic cylinder, and there's a mechanism on the back of the blade we had to operate. So we had 5 unit loads. We put 12 strain gauges on here. So we had strain gauges on the arm and on the back of the blade. And you see those plotted up on the top right here. So the green curves are the measured strains, and the blue curves are the simulated strains once we calculated the loads. And they were thrilled with us. They never would have been able to get any sort of correlation like this. But they said the real problems in development were these forgings here that were on the dozer here, and the welds of the forgings. So they put additional gauges of interest, like this gauge number 19 up against the weld here. And so I've got gauge number 19 plotted up in green here. And then we probed with our True QSE tool the strains and the elements coming away from the weld, and you can see how well we can match these hot spots once we've got the loading and the overall flexibility of the structure right. And this just happens all the time with them. Okay, so guys, I'm gonna drop out of my presentation and we're gonna do a live demonstration here. Okay, so I've got this razor scooter that we've done instrumentation on, and what I want to just show is going through the whole true load process from beginning to end. Okay, so what I'm gonna do is I'm gonna launch the true load pretest software, and I'm gonna just give my true load model a name, and I'm gonna open up an FEA model. This happens to be an Abacus FEA model. And just let it load up here a second. And then I'm just going to load in the loads from the FEA run. So we've got all these loads here on the FEA model. So just to show you very quickly, just so you can see the loads that we actually put on here, let me just go through this very quickly here, and I'll just show you that. So I've got an X load at the foot, a Y load at the foot, a Z load at the foot for my unit loads, and then I've got an X load at the axle, a Y load at the tire patch, a Z load at the tire patch, and we've actually got a drilling moment at the tire patch too. Okay, so these are our unit loads we've put on the model. And now I'm just going to start the true load process here. So I got to select some elements. So I'm going to come in here and pick some elements here. I'm going to get elements on the bottom. And then I'm going to get the elements on the top too. Okay, so we got our element selections here. And what we need to do is we need to kind of get away from the hot spots here, the sharp corners and things of these edges. And so we're just going to do some very quick little things that we can do in true load. So we're just going to go in and we're going to remove the elements from the outside of our selections here. And I'm going to just go in a couple layers here and just do this very quickly. Okay, so you can see we've got our element selections. See, we've gotten away from our notches here. So, because we're trying to find nominal locations to lay strain gauges, okay? And let me just say complete to that. And I've got to do a little bit more refinement on my selection here. So first off, this razor scooter, it's got a double wall in here, and I'm not modeling that fully correctly. So I'm going to just take elements away from that area. So I'm going to just deselect the elements kind of in this zone here. And I'm going to have access issues on the top. So I'm going to get rid of those elements there. Okay. So you can see I've eliminated those elements and I've eliminated the elements. Okay. And let me come back, make sure I've still got that. And then I'm also going to go in, and then back here by the axle, I want to get rid of these elements back here by the axle too. So I'm just going to deselect these back here. All right. And then, and you can see now, I've got an area where my foot's going to go, so I can't put any gauges out where I'm going to be putting my foot. So I'm going to deselect those elements too. So I'm going to come in and I'm going to deselect a bunch of elements on the top there. So I'm going to come in and I'm going to deselect these elements here. Hope I didn't do too many. There we go. And that's pretty good, okay? So now these are my initial candidate elements, and I'm going to do one other little depopulation thing that I'm not going to explain a whole lot of, but I'm just going to say, let's depopulate our selection and let's not have any elements closer than 6 millimeters to each other. Okay, so I basically depopulated my selection to make the problem a little smaller. And the only error I introduce is that my optimal strain gauge is off by 6 millimeters. Okay, I can live with that. And I'm just going to say, let's keep that. And there we go. Okay, so I'm going to just save my model. And now we're going to go find gauges. So we're just going to do this live. So I'm going to say, go find me 7 strain gauges for my 7 loads. And just let it finish up here. All right. And now you can see that we've got the gauges laid. So it found some gauges up here. Okay, some gauges up here on the top, and it found gauges down here. Okay, it's trying to make a little 90-degree rosette, it looks like there. Okay, so we've got 7 gauges for 7 load cases. Ideally, I like my users to have 2 times the gauges for every load. So that would be 14. My data acquisition system only has got 12 channels, so I'm going to go find 12 gauges. So let's go find 12 gauges. So I'm just going to go say, find me 12 new gauges, and let it just go do that. And just let it finish up plotting and finish up the whole thing. Just a few more seconds. All right. And so now you can see the gauge that is found. So we've got gauges up here. Okay. And we've got some gauges down here. All right. So it's got a pretty nice pattern of gauges here. Now, we could go ahead and use the gauge editing tools, and we could move gauges around so I could make things symmetric, and I could do a little bit of work here. I've already done that. I've already collected strain data on this thing. So let me just go and bring in the gauges I've already laid on my model previously. So I'm just going to load in my previous gauges. I'm going to get that one. So now you can see this is the gauge placement I eventually just ended up with. Okay, so I laid 10 gauges on the bottom here, and I kind of made sure that they were symmetric. And I had 2 gauges on the top. All right, so these were the gauges I chose, and I had collected the strain data. And so just bear with me 1 second. I'm going to turn my camera on, and I'm going to show you my real live physical part. So let me just do this real quick, and let's make sure this all works properly here. Okay, so we've got my razor scooter here. Okay, I've got my little data collection system. This is a small little compact data collection system, 12 channels of data, and this is my razor scooter. So I've laid gauges on this razor scooter here, on the bottom, and also on the top up here. So I've gone out and done this and collected real strain data on this thing. And just a word about my razor scooter. My poor razor scooter has made probably 3 trips around the world now. So it's been through a lot. And hold on. And so I've actually lost a couple of gauges on my razor scooter. So when we get to the testing phase here, we're gonna have to take a look at that here. So I'm gonna save my pretest file, and we're gonna go into post test real quick here. And I'm gonna open up my file I just made. So this is the post test module. Just let it load everything up nicely here. And I'm going to grab my test data. And so I'm just going to plot up my test data real quickly here. And you're going to see here that there's 2 channels that are just flat. These are gauges 3 and 4 that are just flat. So I'm going to have to drop them. You know, this actually isn't bad an example because this happens in real life all the time where you lose a gauge. So I'm just going to go in and I'm going to go into my gauge mapping here, and I'm going to drop gauge 3, and I'm going to drop gauge 4. I'm going to say OK, and then we're just going to go. All right, so now we're calculating the loads. So it's really that simple. Load in the model, load in the data, and push a button. Okay, now it's calculating the loads, and it's going to generate an HTML report for us, and it's going to do a bunch of post-processing. Actually, the load calculation is already done. It's just the post-processing that takes time. So I'm just going to minimize this for right now, and we'll just watch it do its work here while it's going through everything. These are the loads, and these are our strain plots, and we'll take a look at those in a minute. All right, and so let me take a look at my HTML report here. So if I look at the overall strain correlation, what we see on the left here, the green curves are the measured strain data that I had collected, and those measured strains were used to calculate the loads, and from the loads then we went back in the FEA model and pull out simulated strains at the gauges. So the blue curves are simulated strains, and then here on the right hand side I've got a cross plot of measured strain versus simulated strain, and we've got a nice nearly 45-degree line. So, and this is with me doing the strain gauge placement, and I'm not a strain gauge technician. So I've got a table showing the percent error per gauge, and then we've got each gauge one by one. So again, the green is measured, blue is simulated, and then we've got a cross plot of measured versus simulated, and we show the gauge on the right there. So we basically are showing each gauge one by one how it's doing, and they all look great, okay? So this gives the confidence that the loads that we've just calculated actually reproduce the strain on the part, okay? So these strains are kind of full field, so we're getting the overall strain on the part right. So now we've got the confidence that the loads are right. And then if we come up here and take a look at the loads, we see the X load at this is the X load at the foot. This is the Y load at the foot. The unit load was positive, so we want the foot load to be negative. So this makes sense here, okay? The Z load at the foot, and now the X load at the foot, and now the Y load at the, this is X load at the axle, I'm sorry. And this is the Y load at the tire patch, and the tire patch was the upwards direction, so we want the tire patch load to be positive. So we got the tire patch load to be positive in the Y direction, and then the Z load at the tire patch, and then the moment at that drilling moment at the tire patch. So we've got all of our loads, and then TrueLoad has then calculated for us created for us a nice true QSE file, and I can just go in and open up that true QSE file that was just created. And now the true QSE file has got our unit load cases and the corresponding loading functions all tabulated for us automatically. And I can plot those up very nicely. And so these are our loads here. And here, let me just take a look at those loads one by one a little bit here. So let me just come in and let me plot up the Y load at the foot and the Y load at the tire patch. And so it's kind of nice. The Y loads at the foot, those are all negative like we expect. And the Y loads at the tire patch are opposite and going positive. This makes good physical sense, okay? So this is very, very good for us. All right. And then let's take a look at the X loads at the foot and the X loads at the axle. So these are the X loads at the foot. So the X load, the positive X direction was going rearward. So the X load at the foot is actually a negative load. and then the tire is actually dragging. So there's actually a dragging force on the tire there, which makes sense. So this all makes nice intuitive sense here that we've got the right types of loading going on. And now that I've got that, I can go in and, for example, I can query. I can go in and query some elements here. I'll say let's take a look at the elements here, and I'll make sure I'm just getting the 2D elements. And let me just find. Let's go take a look at the elements, right in here. Let's go take a look at what's going on there. And I'll say let's look at a vector that's going to go from here to there. So we're going to have a vector along there, and let's go get the strain along that vector right there. And so now we've got this nice strain response on these elements coming away from. So I'm going to turn my legend off here just to make things look a little nicer. Okay, so now we've got the strain response here, and I can say, geez, where's this happening? So I can go in and say, where are you? Okay, you're that element. That makes sense. And where are you? Okay, you're a neighbor. And then what about you? Where are you? Okay, so basically, we can go in and query the part and understand what's going on, and really get a good handle for what's going on with our structure. And so what we can also do now is we can go in and calculate an operating deflection shape or go off to FE safe. It'll take a few minutes to calculate the operating deflection shape on the structure. I've already run that, so I'm just going to pull that up real quickly, and I'll show you the operating deflection shape. Okay, so I'm just going to put this away. I'm going to open up my operating deflection shape file. And let me just make things look a little prettier here. Let me come in here and get stress on Mises. Let me set my value to be 100, my value to be 0, and then I'm going to set this contour undeformed, and I'm going to also say let's show this. And usually I put more of a side load on this thing, but this time when I rode this scooter, I was perfectly balanced. I'm gonna put a section cut on the part here. I'm gonna do this, and let me just see if I can, yeah. We'll just push it back a little bit just so we can see our vector. Just I want to have it look nice, and then let's and also let's set our factor of 10 will be good. Okay, here we go. So now we've got an operating deflection shape on our Razor scooter just from laying 12 strain gauges. So not too bad. All right. So there's our vectors. So you can see the load. It's downward and forward, which makes sense at the foot, and rearward and upward of the axle there. So, okay. All right. So, so now that you've got these types of loads, you can go off and use tools like FE Safe to do fatigue analysis on this, and you can really drive and optimize your design. So this is all about understanding the loading on your product, and you can see how in a matter of 20 minutes here, I was able to go from beginning to end to get the loads in this thing. Okay, So Hisham, that's about it for me for my presentation here. Be happy to take any questions if anybody's got questions.
Well, thanks a lot, Tim, for the extensive presentation of TrueLoad and the live demo. It's really appreciated and nicely done. So thanks again. I have a couple questions that would address mainly the nonlinearities. So how is TrueLoad addressing the nonlinearities, mainly contact and material nonlinearities?
Well, this Razor scooter is a perfect example of contact nonlinearities, right? So the way we deal with a contact nonlinearity is basically you introduce a unit load at the point of contact. So in my example here, my nonlinearity is at the foot, right? The foot can go on or off. So I've got a unit load case at the foot, actually X, Y, and Z directions to handle all the contact directions there. And on the tire patch, I've got loads to handle the tire patch. So you basically model unit loads at your contact locations. And if there's no contact, that unit load will be zero. It will be calculated as zero. And if there is contact, then you'll get a value for the contact. So it's really that simple. It's just part of how we do it. Okay.
Yep. Thank you. One question also deals with the thermal loads. Can TrueLoad combine thermal mechanical loads in one simulation?
Yes. So basically, you just need to put a unit load on your model for it will be a unit thermal load. So it might be, a unit load of 10 degrees or 100 degrees. And then we're going to scale that unit load case up like we do any other load. TrueLoad is really just basically looking at the strain response based on whatever loading you've put on the model. So whether that's a thermal load, a pressure load, or a force load, we're just scaling that up and down. So we'll just mix it in like anything else.
Perfect. One last question will be about dealing with the, oh God, what did I put it? Yeah, so how does the TrueLoad model needs to be calibrated vis-a-vis the experimental test setup?
Well, my customers, and it happens with every customer, okay? The first time they're using TrueLoad, they go through a very expensive testing process to calibrate, to basically put known loads on a structure and see if TrueLoad calculates that same load, okay? And they'll do that, and they do that once, they might do that twice, and then they never do it again, okay? TrueLoad is actually providing for us, we're getting the correlation matrix from the FEA model. So if the FEA model is modeling stiffness properly on the structure, our loads are going to be right. And the real beauty here is that since TrueLoad is generating for us this correlation plot of measured strain versus simulated strain, if we're getting a 45-degree plot like this, that's the calibration right there. Okay, so that is in fact that we're putting the right loads on the model to reproduce the strains in real life. So.
Okay, Tim, I'll thank you. I guess with that question, we'll wrap up the presentation, your presentation and today's Lunch and Learn. So thank you again. Thanks for the Wolfstar Technologies team. Thanks for the Detroit Engineering Product team, and special thanks for the Aventec team for pulling the efforts together for today's Lunch and Learn. I would like to thank two of our clients that they made it here. So thank you so much, guys, for coming along. And thanks a lot for the attendees on the webinar. There were so many from across the US and Canada. So thanks a lot for everybody. And thank you, guys, and have a wonderful day.
Great. And thank you, Hisham.
Thanks, Hisham, for organizing.
Yeah, anytime, guys. And thanks a lot again for the time and the effort. Bye.
Thank you, Sean. Thank you.
I'm just gonna